Section 12.9, stationary points, is sort of one of the most exciting bits about Chapter 12, really. We can really start using our new tool of differentiation and do some maths with it. And the way that we use it is quite interesting. And if you've never seen it before, it's quite an inventive little technique. After a while, after a few months, you'll have used this so many times that it seems old hat. But if you see it afresh, it's actually quite a good bit of mathematical thinking. And it goes like this. First of all, a stationary point. Here's our definition. If you find the derivative of the function, dy by dx, you find the gradient function, and you put it equal to 0, the point where the derivative equals 0, that is a stationary point. Okay? So what does that mean? Well, remember, the derivative gives you the gradient of the tangent at that particular x-coordinate. So if you found an x-coordinate where the first derivative is equal to 0, what you've done is you found a gradient where the tangent has a gradient of 0. In other words, the tangent is horizontal. So that's what my tangent would look like. So I'm going to draw a nice horizontal line in. What could my function look like if my tangent is going to be horizontal? Well, one thing it could look like would be like this, right? It could be a maximum point. Okay. Now in the textbook, you see they call this a local maximum, because if the function actually goes higher elsewhere, then this thing is a maximum. If I look locally, if I just zoom in on that point, it's a maximum. But actually, it's not the maximum value the function ever takes. Okay, so we could call it a local maximum. We tend to be a bit sloppy with the language and just start calling it a maximum point after a while. So that's one option. Okay, the other option I've got is that the function could come down and just touch the horizontal line from above. Okay, so if the first derivative is 0. The function at that point could be like this. The function at that point could be like this. The function could look like this. It could be a flat line, okay? In which case, it's not just a stationary point, it's a whole bunch of stationary points in a row. So, strictly speaking, a stationary point, I would say, is the first derivative is equal to 0, but if you go a little bit left or right of that point, the first derivative is not equal to 0 anymore, okay? So we're not going to count horizontal lines as stationary points, because they're not points, they're lines, okay? And for the same reason, we're not going to worry about functions that properly kind of come up and then go flat for a while and then go off again, because we don't have many of these functions. You know, the equations that we deal with don't produce functions exactly like that anyway, so we're not going to worry about that sort of thing. So we're just looking for single points where the tangent is 0, and these are the sort of obvious two. There is another one, and another one is a little bit tricky to get our head around, so let's just talk about these for a minute. What's happening here is the gradient is positive. On this side, the gradient is positive, and it's getting smaller. The gradient's going down and going down and going down and going down and going down, but it's still positive. Over on this side of the stationary point, the gradient's a little bit negative, a bit more negative, and then it gets really, really negative down here, and it gets quite steep. So the gradient's quite a big negative number, you know, as in a negative number a long way to the left on the number line when I say a big negative number. So if it's gone from positive to negative, it must have gone through 0 somewhere in the middle, and that point there is where it goes through 0. Okay? The word stationary points is referring to the idea of if you differentiate displacement, you get velocity. You may have seen that in the mechanics module or in the end of the video for section 12.8. You could think of it as that, you know, stationary is in the function sort of stops for a minute. Now the problem with that is that there is no sort of duration to this. The x coordinates can't move along. There is one specific x coordinate where dy by dx equals 0. It's not as though the function stops and sort of flattens out, like this example over here. For a stationary point, there is just one point where the first derivative equals 0, okay? So if this was your speed, then this would be a positive speed, a positive speed, a positive speed, a negative speed, a negative speed, a negative speed. So that might be if I threw something up in the air. If I threw it up, it would be travelling upwards and then it'd be travelling downwards. That doesn't mean it stops at the top. It means it's turned from going one way to going the other way. It doesn't mean it has to stop in between. It's just that there's a moment where it's going from a positive velocity to a negative velocity. Same thing here. This function changes from being increasing to decreasing. The first derivative changes from positive to negative, so it goes through 0. We have a tangent which is horizontal there. And then the opposite here, the gradient is negative, then the gradient is positive. Okay, that's a maximum or a local maximum. That's a minimum or a local minimum. Here's the other option. I can have a function which is positive, and it goes smaller and smaller and smaller and smaller and smaller, and then we get one x coordinate where the tangent is 0. So far this looks like it's turning round and turning into a maximum. But what if, at exactly that point, we start getting more positive again? So here, for a maximum, we go from positive to 0 to negative. For this sort of thing, we go from positive all the way down to 0, hit 0 for one x coordinate, and then immediately start trending off to positive again. And I could flip that round and say we get a negative gradient, then hit 0, and then get more and more negative again. These things are called points of inflection, okay? And that's where we get led to this table. So if f dash of x is 0, we have ourselves a stationary point. That's the middle row. If you go a little bit to the left of this x or a little bit to the right, if you get a local maximum, the gradient's positive to the left and negative to the right. For a local minimum, it's the other way around. For a point of inflection, the gradient is the same sign, but the negative here and negative here, or positive here and positive here, okay? There's no sign change in the gradient if you have a point of inflection. So that's what we mean by a stationary point. We can find a stationary point by putting dy by dx equal to 0 and solving the equation. And then we can classify stationary points, and we're going to worry about that in a little while. So let's just start with a quick look through example 17. Find the coordinates of the stationary points of the curve with this equation. So just part A. We're going to look at part B in a minute. So part A goes like this. There's my function, there's the derivative of the function. If I want the stationary points, I put the derivative equal to 0. When I put the derivative equal to 0, I can solve that equation, and the way I'm going to solve this one is by factorising because it's a quadratic, and I get 2 different x-coordinates. But what we want is the stationary points, and what I have now is the x-coordinates of the stationary points. How do I find the y-coordinates? One thing we know about the stationary points is they are on the function, right? They're on the curve. So if they're on the curve and I know the x-coordinate, take that x-coordinate and put it into this equation here. When you do that, 2 times 1 cubed minus 15 times 1 squared plus 24 times 1 plus 6. That's that calculation there. That's where the 17 comes from. When x equals 4, 2 times 4 cubed minus 15 times 4 squared plus 24 times 4 plus 6. That's this calculation, y equals minus 10. So the stationary points are the point on the curve when x equals 1, when y equals 17, that is 117. The point on the curve when x equals 4, at that point, y equals minus 10, so that is this point here, 4 minus 10. So we can find stationary points. Differentiate, put the derivative equal to 0. Now, how do we know if it's a maximum or a minimum or a point of inflection? What we could do is take a small amount, an h. So here, where f of x equals 0 and x equals 1. So I could try x equals 1.1 and x equals 0.9. I could substitute both of those two into the equation for the derivative, and I could see what the gradient's doing either side. And if there's a sign change from positive to negative, it was a maximum. From negative to positive, it was a minimum. If it's negative and negative or positive and positive, then it's a point of inflection. So there's an option, okay? That's not a particularly appealing option for 2 reasons. One, it seems like it's a lot of work. And 2, how do you know what a little bit is? I decided there that 0.1 counts as a little bit, but if I just change the scale, maybe 0.1 is a huge leap, and maybe there are all sorts of ups and downs between, you can imagine a function that does this. There's a minimum, and then a maximum, and then a minimum, and then a maximum, and this whole thing could be, if this is 1, 0.1 could be, 1.1 could be over here. 1.1. So the gap between 1 and 1.1, that gap of 0.1 could be from over here to over here. So who knows what's going on? If you pick a little bit, what counts as a little bit? Well, there's no mathematical definition of a little bit, or at least there's no simple, easy one that we can use. So that's not how we're going to deal with whether it's a maximum or a minimum or a stationary point. So what we're going to do is we've got a clever idea, and that's in this blue box up here, and I'm going to explain it now. So the typical question is exactly like example 17. Find the stationary points. We've done that. The way they've phrased it in part B is determine the nature of the stationary points. Another way of phrasing that is find and classify stationary points. If you're looking this up in revision guides or anything, finding stationary points, classifying stationary points, those are the two key skills you've got to have, okay? So finding stationary points, first derivative, put it equal to 0. Great. Classifying stationary points goes like this. So here's my function. If my function has a maximum, then let's take the same x-coordinate, okay? So my x-axis is here. I'm not going to worry about the y-axis. I'm just going to take that x-coordinate down. And let's imagine, you know, this is x equals 1 for this example here or something. This is the x-coordinate. Let's look at the same x-coordinate for the derivative. I don't know where the y-axis is exactly, but what I know, what's happening to the derivative, it's going from positive to negative. Okay, the derivative here is positive, the derivative here is negative. So a little bit to the left of the stationary point, a little bit to the left of the maximum, the gradient function, the derivative is here. A little bit to the right is here. So where the maximum is, just very locally, you know, it's a small distance around it, the derivative's doing that. Now, we've just said there's no mathematical definition of what we mean by a small distance, but what we mean here is what as small as it needs to be. If the gap between here and here is 0.1, then this gap here is 0.01, I don't know. If the gap between here and here is 10, then I've just drawn something here where that gap is 1, right? If this is a maximum, a little bit is defined by whatever the x scale is in this graph, sort of carries through to this graph. So locally to this maximum, the gradient goes from positive to negative, so the derivative looks something like this. So the second derivative, well, the second derivative at this point is going to be negative, isn't it? Because it's going from above the x-axis to below the x-axis, so this is going down. So the second derivative has to be negative. Let's have a look at what happens with a minimum. With a minimum, again, I'll take that same x-coordinate. Here, the gradient goes from negative to positive. So if it's going from negative to positive, close to that stationary point, that is what the first derivative is doing. And if that's what the first derivative is doing, then the gradient of the first derivative is positive at that x-coordinate there. And the gradient of the first derivative is also called the second derivative. So if I have dy by dx equals 0, and the second derivative d2y by dx squared is less than 0, I've got a maximum. If I've got dy by dx equals 0 and the second derivative greater than 0, I've got a minimum. And you would think then, wouldn't you? Point of inflection, we should have, well, less than 0 is a maximum, greater than 0 is a minimum, so that only leaves being equal to 0. And that is going to be true, but with a few extra caveats that we're going to have to worry about as well, okay? Point of inflection, let's just have a look at a point of inflection. The gradient goes from very, very slightly positive to very, very slightly positive. So at the point of inflection, the gradient's sort of doing this. It's positive, comes down to 0, and it goes back up to positive again. So you can see it sort of flattens out a little bit. And so the gradient at the second derivative could be 0, couldn't it? Okay? Now, the problem with that is, how much does it flatten out? Okay. Now, when I was taught A level, it was enough to say if the second derivative is 0, it's a point of inflection. And since then, they've changed it 2 or 3 times, and I think it's even slightly different on different boards at different times. When you have a point of inflection, you could have a point of inflection that's sort of like that, and it just, you know, it's a very shallow point of inflection. You can have a real point of inflection that really sort of flattens down and then zooms off again. And depending on how big a deal it is, depending on how flat the point of inflection is, different things can happen. So you can end up with a problem here, okay? You can also have a minimum that does that, or you can have a minimum that really sort of slowly flattens off and then takes off again. And at that point, you can have a minimum where the first derivative is flat and therefore the second derivative is 0. So we have to worry about these things. There are different techniques for dealing with it. There's sometimes you can look at the third derivative and there are techniques like that, but all that they want us to do for this exam, this syllabus, is this. They just want us to look at a little bit either side. So they want us to do it through this method. So if the second derivative equals 0, the point could be a local minimum, or could be a local maximum, or could be a point of inflection. Mostly it'll be a point of inflection, but we need to check. You need to look at the points either side to determine its nature, and that's like this, okay? So same as it was in example 16, part B, when we didn't know this stuff here, when all we knew was this stuff here, we just had to take our x coordinate, go a little bit to the right, a little bit to the left, and look what happens to the first derivative. The fact that we still don't have a good mathematical definition of what counts as a little bit, we're not going to worry about too much. They've taken 0.1 in the example. I think you're always going to be able to use 0.1. Okay, just use a small number. 0.1 is small enough for practical purposes on the questions they're going to give us that if you just get in the habit of 0.1 to the left, 0.1 to the right, that'll do the job, I think. If you're feeling really fussy, make it 0.01. The reason I can't say that will always 100% always work is because we always have to take into account the fact that there might be a sneaky examiner there somewhere who's looking for a difficult, A-star standard question and turns that, that's a rule of thumb I've given you that's going to work almost always. And that's always a place where a sneaky examiner can say, right, I'm going to try and, test whether they understand. Why are you adding on 0.1 and taking away 0.1? Is 0.1 always going to be a good amount or not? And the answer is, as long as 0.1 counts as a small amount in the context of the function that we're looking at. I don't know how the examiner would turn that into a question exactly, but we understand that mathematically 0.1 is only a small number relative to the other numbers involved, okay? So this technique is the one that we've got to use if we're looking at points of inflection. What they've summarised in the black bullet points here and what I summarised here is how we deal with maximums and minimums.